Okay, sweet. So I think today we'll just go ahead and start up with Anki, and then we'll just go straight into the practice. I'm wanting to spend more time practicing, because at present, I feel like what's holding me back presently is just a little bit more deep of an interaction with the practical side of things. Um, yeah. Yeah, so I think we'll start here and then we'll go ahead and try to dive deep there on the test. And yeah, I guess we'll go from there. Okay, mean value theorem. It needs to be continuous on a closed interval and differentiable on an open interval because if it is the case that we're going to get the slope of the tangent line at a given point between the 2 points, then it has to be differentiable. And then continuous, if it's non-continuous, then it could explode, meaning the tangent line could not be let's see, let me describe Excalibur. So if it was non-continuous, like this point in here and here, this point here and this point here, then it would not there are slopes here that would not be represented as the mean of these 2 points. And so it has to be continuous. Okay, I'm going to send that one through. The fundamental theorem of calculus is that integrals and derivatives are inverse functions. Okay, a definite integral and antiderivative. So a definite integral is when you take 2 antiderivatives and subtract them to actually find the volume underneath the curve. Okay, we're gonna attend to this one later, because this one I don't think was specifically in the yeah, we'll look at that one later. I'd like to spend a little more time on this stuff. So horizontal asymptote. Let's see. I think we'll actually go through the asymptotes section again as well, because I hadn't done any practice with that, so I don't really have a deep understanding. So I prefer when using Anki to not have Anki be the source of learning something, but rather be the source of reviewing something. It's much better for understanding to learn within the context or within the full context, rather than just some atomic question and answer approach. So let's get on this here. Okay. Okay, so I now know for this one. Maybe we'll. I need to. Need to pull up the calculus. Okay. Okay, maybe we'll just write out calculus exam 1. Okay. So we'll zoom in here so you guys can see. Should probably make this oh. Okay, so like that, and then we'll bring this guy here. Perfect. Now we have everything. Perfect. Okay. Awesome. So for this first one, I think what I'm going to do is write out the approach that we take for solving these problems. I think that may help because and I'm going to ensure that I know, like I know that I could describe the solution, or maybe we're just writing out this. Yeah, I'd say we're writing out the solutions. Okay. So one, and then consider the function, and then the first part. No real numbers are discontinuous. Well, is that the case? I feel like we would have a discontinuity right here. Okay, we're gonna review this one. I believe it is the case that no numbers are discontinuous. Okay, so I would think that this type of discontinuity of the piecewise functions is the type of discontinuity I was assuming that we were going to have, that it was going to be at that break, which would make sense because we're dealing with two different functions depending on the. So for this, I need to learn how to calculate the limit from 2 points, so from two sides. So I know I could just substitute the limit in, but I'm not sure what it looks like to calculate the limit from the upper side. So if x is greater than pi, then we do this. If x is less than or equal to pi, then we do that. And so yeah. But yeah, I'm not sure how to use. Oh, wait a second. Okay. Never mind. This is like fairly obvious. So for x is greater than pi, then we have this function. So this will be. We will use this function until it equals pi, and then we use this. So we could literally, like, the limit approaches pi here, and the limit approaches, like, the limit of pi would also be reasonable here. So if we just take the limits of both of these functions and they're not equivalent, then then we have a discontinuity. Okay, so maybe I just pull up a calculator or something. Calculator. Okay, so we're gonna do the sine of pi. Pi equals 0. Okay. What if we do like the sine of 3.1? Okay. And I feel like knowing sine is 0 at pi would make sense. Oh, actually, we may... Wait a second. Oh. No, actually, we do not have a discontinuity. I've revised my statement. Because at, like, sine of pi is apparently 0. And then x minus pi. So if this is equal to pi, then it's also 0. And so these transition, like, perfectly. So I would say, man, I feel, that this is a tricky one because it tells me there should be real numbers that are discontinuous. Continuous. For the function. Okay, no real numbers are discontinuous for the function. It is continuous. Because as... Okay, it is continuous because as the limits of either function, or no, it is continuous because the limits of either function used when approaching the transition are equal. Okay. Identify the horizontal and vertical asymptotes of f of x. Okay. Vertical asymptotes. Okay, now we'll just learn how to identify vertical asymptotes. Okay, actually, we got to think about this for just a little bit. So we have a vertical asymptote when y gets incredibly large. No, let's see. No, when x okay. So we have a vertical asymptote when... Oh, I don't want to do that. I want to do white. We have a vertical asymptote when... And I think it would... Where, as we approach a given point, y gets arbitrarily large for a given x, and then depending on the type of asymptote, maybe it like looks like this. So I don't know if we have. Okay, yeah. So let's try to resolve it and then get some feedback and then see where we're at. Okay, so I don't believe this has any horizontal asymptotes. Sorry, vertical. Let's see. Set the denominator equal to 0 and solve for x. The x value that makes the denominator 0, but not the numerator, is a potential vertical asymptote. Okay. So we don't have a yeah, I don't believe we have a vertical asymptote here. Because we don't have a denominator. Okay, but this is important, and I do have a card on this now. Okay, so we don't have a vertical asymptote because denominator. I don't know if that's a great explanation. Denominator. So can you have a vertical? Actually, let's just think about this. Okay. Okay, so I need to have an understanding why for... So I'm going to... right now, I don't have an understanding why when it's the case that when we have a denominator that emerges vertical asymptotes. My reasoning for this presently is that if I have a denominator that is like x minus 2, and I have x squared minus 4. The issue I'm having with, so what for these vertical asymptotes that are shown, these like approach infinity, or like these approach infinity until they hit like this point. But if I like put, if I do 1 here, or let's see, 1.5 maybe. Actually, yeah, I guess we have to do 1.5. Anyway, so we get like, what is that? Okay, well, let's see. Okay, so let's see. Graph a function asymptote and describe how this asymptote how this asymptote can be found mathematically. Oh, actually, no, this makes tons of sense. Oh, that's so interesting. Okay, so this is a good cognitive tune here. Try to find the simplest, when something isn't making sense, try to find the simplest example of it. Because now this is making sense, right? So if I have 1 over 1, or over, sorry, if I have 1 over x minus 1, as, so if I have 1 for x, obviously this is undefined, so at that point we don't have anything. But if I have 0.5 for x, or let's see, if I have 0.1 and then 0.5, and then 0.7, so 0.1 would leave me with, let's see, like negative 0.9. And so 1 over a decimal is larger than itself, right? And so if I have, in the same case, if I have 0.5, that's dividing by 0.5 would create a larger number still. And so as I arbitrarily get close to 1, it becomes infinity. Okay. That actually makes sense now. Okay. I'd like to capture that in an Anki card. Asymptotes can be found through understanding through vertical asymptotes can be found through a sort of like an observation of denominator and numerator. Through observing, maybe observing the denominator through considering the denominator. I don't know if that's a great question. Use f of x equals 1 over x minus 1. Okay. Let's see. So I'm going to have some restate, include why it is a vertical asymptote. Nicey, nicey. Okay, this is good. Okay, so we are on to the next one. Nope, we have to do the horizontal asymptotes now. So, okay, so actually, given my understanding so far, can I derive how you would find a horizontal asymptote? So, I believe horizontal asymptotes would look the exact same, but of course, like opposite, like in terms of the interaction between x and y. And so let's look at an example and see if we can pull that out. So I'd hit a Okay. And I'm realizing that this actually doesn't have a vertical asymptote. It has a whole discontinuity because you can factor out x minus 2. So it's x plus 2 above. And I guess another thing for finding vertical asymptotes only functions where as x increases, like the bottom is actually. No, okay, I need to stop thinking about like multiplication. Because when we're dividing by when we're dividing by a decimal, it increases the numerator, right? Instead of decreases when it's like a larger or greater than 0, right? Or greater than 1. Okay, so this one actually I think will asymptote. Yeah, because as this one down here gets like arbitrarily close, so it starts after the result of this is less than 1, then it starts causing this guy to get arbitrarily large. Okay, reasonable. Okay, so I wanted to figure out if I could determine what the what it would look like for a horizontal asymptote. So I'm not sure. I guess it'd be like something. Well, let's look at an example. Horizontal asymptote. Okay. Oh, okay. So I guess we have vertical and horizontal asymptotes here. And so what allows me to say this is a horizontal asymptote? So there is, as x approaches infinity, y will approach a given number. Sorry. No, that's... Okay, no, that's correct. And then conversely for vertical asymptotes, as the denominator reaches the limit, or I guess as the result of the denominator gets close to 0, but is not quite there, it approaches infinity. So for this one, so as my x gets larger, I just merely approach 2. So we'll substitute 10 here. So 10 minus 3 is 7. 10 times 2 is 20, so that'd be 20 over 7. Okay. Yep, that's about half there. So it's approaching 2. So as just my relationship is such that it'll find that he asymptote. I'm not exactly sure I'm not exactly sure of the required relationship for something like this. And so let's okay. Yeah, let's determine that, and then I think we'll end there. Okay, well, so we'll just say how to find the horizontal. Asymptote. Okay. To find the horizontal asymptote of a rational function, compare the degrees of the numerator and the denominator. So if the denominator's degree is higher, then the asymptote is 0. If they're equal, it's the ratio of leading coefficients. If the numerator's degree is higher, there's no horizontal asymptote. Okay, so looks like there are just 3 different types here. And I think when they're talking about degrees of the numerator and the denominator, my initial guess is that actually, I don't know if they're talking about degrees of freedom. Or this is like dealing with exponents. I think this is, yeah, I'm not sure what the, okay, looks like numerator degree is 3 and denominator is 2, so it looks like we're dealing with just the exponents. Okay, and then I'm going to make sure that we have a card that is on horizontal exponents. Exponents. Horizontal exponents. Okay, maybe I do not have. Horizontal exponents, what? Horizontal asymptotes. Okay. Okay. One thing I want to know is why they specify that it's for a rational function. Okay. So, for rational functions. So I'm asking if we have the same issue for vertical asymptotes where we typically specify that it is for a rational function. Okay. So we're going to do vertical here to make sure we have that clarification. Okay. Feeling pretty good about that. And then we will be on to... We'll have to identify them. I don't believe we have any here. Actually, from the description was given, we have 0 of them here. And then, okay. I know that one. So this one's about the mean value theorem on the closed interval of pi 2 and pi 3. Or pi times 2, I guess. Pi times 3. I don't know how that's verbally described. Find the limits. Okay. I think these will actually be not that bad. Okay. Consider the function, state the domain and range. I think I will need some additional looking into for that. I feel like I'll be able to find the first degree and the second degree derivatives. The local extrema. I'll have to jog my memory for that. But I believe I know. Find all the values of x where f of x has an inflection point. Okay, I think I can do that. Sketch the graph. Okay. Okay, and then this one's about find the linearization of RT. Okay, it looks like we're finding the slope of the tangent line there. I think that's what they mean by the linearization. Use the linear approximation. Okay. Consider the curve. Approximate the area of the curve. Okay, so I know what this means. I know what, but I'm not sure how to do it. Actually, I think I might be able to do this one. Because I only have 4 rectangles, and it's literally like 1 through or 0 through 4 here, or 0 to 4. Yeah, I actually might be able to do that one. Express the area of the curve as the limit of Riemann sum. Okay, so I just need to write up what that looks like there. Find the exact area. Okay, I think I should be able to do this. By just using a definite integral. Is the Riemann sum an approximation of the area under the curve? Okay, I'll be able to answer that one. And then evaluate. That looks like hell there. Okay, so I was kind of like a little worried that I did not have everything going as I'd like for like the practical stuff. But I think if like I'd like to. I think I'm gonna spend time this weekend because I'm running into the issue where like I'll begin working on something, and then I'll get through my Anki, and then I'm not able to make much progress on the like procedural stuff because of how much time Anki takes. But I can't avoid doing Anki, so I guess what I'm saying is I benefit more from a longer session. And actually, I don't think I feel the same issue when I'm learning at a conceptual level, or at least I didn't when I was doing that. But for procedural stuff, I feel like I want to dive into it more. I guess that's just my feeling right now. So anyway, I'm feeling actually really good about that now. I think we will end there and we will restart tomorrow. And then I'm going to find a time next week for that. So yeah. Okay, sweet. I'll see you guys later.